Review of the topic related rates. We're going to dive right into a problem here. This one says we've got oil spilling, it spreads in all directions. It tells us that polluted area is circular, and we are asked how fast the area is increasing. When the radius is 30 feet and the radius is increasing at a rate of 1/6 foot per second. So because we have a circle, we know the area of that circle is pi r squared. Because we're looking for the rate of change of the area, we need the derivative, but we want to know each second how much is the area increasing by. So when we take the derivative here, we want to know the derivative dA, not as it changes per meter that the radius changes, but how it changes per unit of time, which in this case is seconds. So we want to take the derivative with respect to time. So when we take the derivative of this side, pi is a constant, so I can just move the 2 out front, subtract 1 from the exponent, and then the chain rule says times the derivative of r. Because we took the derivative with respect to time, the derivative of r is not 1, it's dr dt. Now I can plug in the radius, which is 30. And dr dt is the rate of change of the radius. It is getting bigger, so it's positive, and it's 1/6 foot per second. 30 times 1/6 is 5, times 2 is 10. So we have 10 pi. Units for dA dt would be units of area, which is feet squared, over units of time, which is seconds. This one here is kind of the classic related rate problem. We've got a ladder laying against the side of a house. It is sliding, the base of the ladder is sliding away from the house. So house, ground, ladder. This side is sliding away from the house. As that slides away from the house, this is going to slide down the wall. We are asked how fast is the top of the ladder sliding down the wall when this side is 12. So as this side slides away, this triangle here, this side of the triangle changes. It gets bigger. So we have to call it a variable, x. As this slides down the wall, this side of the triangle changes. We have to call it a variable y. As this slides out and this moves down, the length of the ladder here does not change, so I do not need to call it a third variable. Instead, I can go ahead and fill in its numerical value because it's a constant through the whole problem. Come up with a relationship between your variables. In this case, we're going to use the Pythagorean theorem. X squared plus y squared equals 13 squared. We're looking for the rate at which this side is changing per second, so we're taking the derivative with respect to time. 2x dx dt plus 2y dy dt equals, this is a number, derivative of a constant is 0. Fill in what we know. We are looking for the rate of change of this side when the base of the ladder is 12 feet from the house, so x is 12. The base is moving away from the ladder, or away from the wall at a rate of 0.2 feet per second. They don't tell us why. They don't tell us this side here. So what we can do is we can plug 12 in for x and solve for y. You'll find that y is 5. And then solve for dy dt. That's a plus. And you'll get dy dt equals negative 0.48. It is negative because this side here is decreasing in size, because the side of that triangle is getting smaller. It wants to know how fast. When it asks how fast, we don't necessarily include the negative there. So 0.48 feet per second. And there's some related rates for you.